your program manages a bunch of related data, like a user's favorite songs. You start by creating a variable for each song name, but that quickly gets out of hand. You might have 5 songs, then 100 songs, then 1,000. How can you keep track of all those variable names? This calls for our first data structure, lists. A list allows us to store a bunch of data in a single container, which we can then refer to with a single variable name. To define a new list in Python, we use square brackets. This creates an empty list named songs. Then we can just stick data in here, separating each individual piece of data or element with a comma. Here, our elements are strings, but lists can hold values of any data type. They can also hold duplicate elements, so this song can appear in the list twice. In Python, a list can even hold values of different data types. Lists store data in an ordered sequence, which means the ordering of the data in the list matters. This list and this list are not equivalent. Even though the data is the same, it's in a different order. Okay, we've organized the data into a nice container, but what if I want to access the individual songs? Remember when I said the order is relevant? We refer to the individual elements based on their position in the list. This is the first element, the second element, the third element, and the fourth or last element. But in computer land, instead of starting our count at 1, we start counting at 0. We call these positions list indices. So the element espresso is at index 0, this is at index 1, index 2, and index 3. The syntax for accessing an element at a specific index also uses square brackets. We take the variable name of the list, square bracket, index, square bracket. So this accesses the element at index 0. Back to our program. If I access an index that doesn't exist, then I get an index error, which is a type of runtime error. This list only has 4 elements, so if I try to access the element at index 7, there is none. So the computer rightfully throws up its hands and says, I don't know. To protect against this, we can always compare an index to the number of elements in the list. If we remember our built-in length function, which we use with strings, we can also take the length of a list, which just returns the number of elements. So the length of this list is 4. Since we start counting indices at 0, however, that means the last element of a list is at the index length of the list minus 1. In this case, 3. So if we want to know if an index is valid, we just need to check if it's between 0 and the length of the list minus 1, inclusive. Okay, what about replacing values? A list is what we call a mutable data structure, which means we can modify it after it's been defined. We can update the value at a specific index using an assignment statement. On the left-hand side of the equal sign, we put the name of the list, square brackets, and the index we want to mutate. Just like any other assignment statement, on the right-hand side, we put the value we want to store. And we can also write a self-referencing assignment statement where we grab the current value, modify it, and store it back in the same location, which we can also write with our plus equals syntax shortcut. Either way we write it, we can see that we modified the element at index 3. We concatenated those exclamation marks. To review, we can use a list to store multiple values in a defined order. We access values based on their position or index, which we start counting at 0. We can get the number of elements in a list using the built-in length function, where the last element of a list is at the index length of the list minus 1. And if we access an index beyond that, we get an index error. Let's trace how the computer stores and updates a list in memory. Here, we have an assignment statement with a list definition on the right-hand side. So just like when we defined variables before that held primitive data types, the computer goes off to short-term memory, allocates space for the new list, and tags it with the variable name wave. But how exactly does the computer represent that list in memory? In Python, lists can hold values of any data type. Your elements might be integers, strings, or even other lists. We'll also learn that you can add new elements to a list after it's defined, so the length of your list may change as the program runs. All that to say, the computer has no idea how much space it's going to need in memory to store that list over the course of the program. So instead of allocating a giant chunk of memory and storing all the elements of the list there, the computer instead just stores the individual elements wherever it wants. This is more efficient because depending on the program, other things may already be stored in memory. And it's easy to find a bunch of small chunks of memory scattered around, but it may be hard to find a giant contiguous chunk. It's like if you're packing a suitcase. It's easy to find small bits of space for a phone charger or an extra pair of socks, but it might be hard to find a contiguous chunk of space to throw in a pair of boots. You might have to shuffle everything else around first. Okay, but then how does it find all those elements if they're scattered around in memory? Well, it allocates a separate small chunk of memory whose job is to point to the locations where the elements are stored, just like a directory. The variable name then points here. Specifically, it points to the first slot, which contains the location for the element at index 0. That's why indices start counting at 0. They're offsets from this location in memory. Phew, okay, so we know how that list is stored. Let's move to the next line. We always evaluate inside the parentheses first, so here we're accessing the variable wave. The computer looks that up in memory, and then the index in the square brackets tells us the offset from this initial location. So 2 means we're 2 slots over. That slot, again, just contains the location where the actual element is stored. So we follow that way down here and grab the actual value. We substitute that in back up here, and now we just have a print statement. So we print that value to the console. Next line, we have an assignment statement. So we simplify the expression on the right-hand side first. We can see that we're referencing the element at index 1 on both the left-hand and the right-hand side of the equal sign. So this is a self-referencing assignment. We're grabbing the current value, adding 0.3 to it, and then storing it back. Our access here goes off to find the variable wave, moves over by an offset of 1 this time, and then follows that pointer to where the value is actually stored. We substitute that value in, add 0.3, and get a single value, which means we're ready to store. To start, the computer allocates a new chunk of memory and stores the float 0.72. But now it needs to tell the list about it. The assignment statement wants to update the element at index 1. So we go to our variable wave, move over 1, and then update that memory address to point to the new location where we just stored 0.72. Done. And now that that old value has nothing pointing to it anymore, the computer will come back in and clear out that memory. We load in our next assignment statement, and we simplify down the right-hand side. In the order of operations, the computer treats square brackets basically the same as parentheses. So we start evaluation with the innermost set. First, the computer evaluates this length function call. The length of a list is just the number of elements in it. So here we have 1, 2, 3, 4. Note that while the indices start counting at 0, the number of elements is still 4. Anyway, we substitute in that 4 here and we subtract 1. Now we just have a standard access. We find the variable wave, move an offset of 3, follow that pointer, and end up here. But instead of duplicating that value and copying it to a second location in memory, the computer optimizes, and it just has the variable sample point to the same location. Okay, now what do you think happens here? It's just a standard variable assignment. So we allocate a new chunk of memory, store the float 0.65, and then move the variable sample to point to this location. Important point, notice that this does not affect the list wave. At index 3, our little directory up here still points to the value 0.4. We only moved the pointer for sample. Last line, we grab the value for sample and substitute it in. We're ready to store, but where? Well, the left-hand side tells us to go find the variable wave, and then move an offset of 8. 1, 2, 3. Okay, and we ran out of slots. So what happens? That's going to be an index error. So the computer will display that in the console, and then immediately terminate the program because it doesn't know what to do. And as always, when we terminate a program, the short-term memory gets cleared. Zooming out, the computer does make a few other optimizations here and there when storing lists in memory. For example, it actually pre-calculates and stores the length of a list, so it doesn't have to count the number of elements each time. There is a whole field of study in computer science dedicated to optimizing, evaluating, and comparing the efficiency of data structures, like lists. But for now, let's focus on how to use lists in our programs before we go too deep on the theory. You have a list of related data, but now what? Well, in most cases, you want to operate on every element in the list, whether that's searching for particular values or modifying every element. Let's start by doing this the hard way. Say I have a list of test scores, and I want to count how many are above or equal to 90. Well, certainly I can access the test at every index individually and do that comparison. But I'm repeating myself a lot. And if I add more test scores, then I'll have to go in and add another one of these checks. This problem kind of looks familiar. How did we solve it before? We use loops. All right, so let's apply what we know about loops to iterate over the elements of my list. We want to go through every possible list index and access the element there. Indices start at 0, so let's initialize our loop variable to 0. And on each iteration, we'll increment the index by 1. A quick reminder on our plus equals syntax shortcut for self-referencing assignment statements. This is equivalent to index equals index plus 1. Okay, but when do we stop? Well, when we get to the end of the list. We know that the last element of a list is at the index length of the list minus 1. So that should be our last iteration, which means we want to stop when index equals the length of the list. Then we just move that conditional inside the loop body, so we do that comparison on every iteration. And since I generalize my loop to stop based on the length of the list and not a hard-coded value like 4, my calculations still work no matter how many tests I have in my list. Now, if you're like, hey, why are you making me use while loops? You're absolutely right. We typically do list iteration using for loops because it's less code. You may have wondered before why range starts at 0 by default and why its stop value is exclusive. It's because it was invented for this exact situation, lists. Instead of putting a hard-coded value as the stop argument to the range function, we can pass it the length of the list. So it'll start at 0 and it'll stop when the loop variable index reaches the length of the list. Wow! By convention, we shorten the loop variable name to I if it represents the index of a list. We move that conditional inside the loop body, and once again, we have an equivalent program, but with even less code. But can we go deeper? Programming language developers recognize that programmers will very frequently want to iterate over the elements of a list. So many of them invented a syntax shortcut called a for each loop, that is, for each element in the list. In Python, we have the syntax, the keyword for, the loop variable name, the keyword in, and the list to iterate over, followed by a colon. We call this iterating by element versus iterating by index like we did before, because here we're not using the index directly. The for each loop automatically updates the loop variable to contain the next element in the list on each iteration. So on the first iteration, the loop variable grade will contain the element at index 0. On the second iteration, grade will contain the element at index 1, and so on until it reaches the end of the list, where it automatically terminates the loop. Note that the loop variable here represents an element of the list, not an index, so we want to make sure we name it descriptively, based on what each element represents, not I. If we move our conditional inside the loop body, we have an equivalent program again. So now that we know this, why would we ever want to iterate by index? Behind the scenes, the for each loop is copying the value of the element into the loop variable. It's not keeping a two-way link back to that location in the list. So if I want to modify all the values in the list, I can't use a for each loop. All this does is update the value stored in the variable grade. It doesn't modify the original list. To modify the actual list, the left-hand side of the assignment statement must be a reference to the list itself. That means we need to iterate by index if we want to modify the list. That way we can use the indices to access specific locations in the list and reassign their values. Like maybe the teacher decided to curve every test score by 5 points. You might also want to iterate by index if the indices of the list are relevant to the calculations. Like maybe you only care about every other test score. But whether you're iterating by index or by element, loops give us the power to easily go through every element of a list. Let's design a program with lists. Say we've been tracking our screen time usage on our phone, and we want to take a closer look at that data to better understand our usage patterns. I want to know how many minutes I spend on my phone every day, and how many separate times I pick up my phone to do something, which I'll call screen time sessions. The tracking software I'm using formats my data in a list, where each element represents a minute of the day. Each minute, it records the name of the app that I'm using, or if my phone is idle, it records an empty string. Here, I've downloaded the data for a single day. I can split a long list like this over multiple lines, as long as I start and end with a square bracket, just like we do with parentheses. This quickly clutters up our program, so it's good practice to put our data in a separate file. Then anyone who needs the data can just import the module. Now for our data analysis. Let's create a new module to put all of our functions. We'll start with a function to count our total minutes of screen time. It should take in as a parameter a list of that raw usage data, and it should return out a count of the active minutes. Now, the total number of minutes, of course, is just the length of the list, but we don't want to count minutes where the phone is idle. So we'll start by iterating over the list and keeping a basic count. Since we don't care about the particular index, we can just iterate by element. We'll initialize our count to 0 before the loop, increment it on each iteration, and return its final value. But we don't want to count every element. We only want to count the minutes where we're using an app. So if the element is equal to the empty string, we can skip it using the continue statement, meaning we immediately jump to the next iteration without executing this increment line. Okay, let's test our function. We'll go back to the main file and import our screen time module. We can call our count minutes function on our real usage data, but how do we know if this number makes sense? Instead, let's try calling it with some smaller test cases where we can actually verify the answer. If every minute is idle, we should get back a count of 0. If some minutes have an app name, we should count just those. And if all minutes are active, we should count all of them. One quick thought though is that some of my screen time is mandated, like I have to be on this Zoom call for work. I'm mostly interested in my personal screen time. So what if I had the option to specify apps to exclude from my count? I can add a second parameter that takes in a list of apps. And if I want to count all apps like before, I can pass in an empty list. So back to my function definition, I'll add that new parameter. And then during our list iteration, we want to skip that element if it's one of these apps. We can use the in operator to check if our current app is in the list of excluded apps. All right, next analysis. Let's write a count sessions function. It should take in our list of usage data and return out the number of distinct phone sessions. So if I check my email, listen to some music, watch some videos, message a friend all in a row, that all counts as a single session until I take a break from my phone. As we iterate over the list then, we know we started a new session if our current element is an app name and our previous element was an empty string. There are several different ways to implement that logic. Here, I'm going to use a variable to keep track of the previous element. At the end of each iteration then, we just set that variable to the current element. But what do we initialize previous activity to? Well, our interesting test cases here will be when there's idle time at the beginning or end of the list, versus when the first or last element is an app name. Does our function correctly count the first and last sessions? If the first element is an empty string, we don't want to count a new session. Log not equal to the empty string will evaluate to false, so we'll correctly not execute this increment. However, if the first element is an app name, we've started a new session, so we do want to increment the count. That means we need this condition to evaluate to true on the first iteration. We're covered on the current element not equaling the empty string, but if we want this whole expression to be true, we need to initialize previous activity to the empty string. Then we just need to verify that those two test cases with the last element work. And our function is done. Last piece, I want to know my average session length. That is, how many minutes I spend on my phone at a time. To calculate that, I can just divide my total minutes of screen time by my number of sessions, which conveniently I already have functions for. So we'll nest both of those function calls, divide them, and return the result, which I'll round to the nearest whole number. Let's run through our test cases again. And we have a 0 division error. So if we're dividing by 0, that must mean our number of sessions is 0, which might be a valid case if we're offline for a while. To avoid the error, we can just check if the number of sessions is 0, in which case the average session length should just be 0. Based on this day's results, maybe I decide I want to spend less time on my phone per session. Or maybe I decide to expand my analysis, whether that's excluding work apps from my session calculations too, or downloading more of my usage data to compare results across multiple days.